Everything you see around you will one day be gone, not just for millions, but for trillions upon trillions of years. The final fate of all matter is a story written in the laws of physics, a slow cosmic transition that leads to an end beyond our wildest imagination. By the end of this journey, you will understand the ultimate timeline of our universe, from the last flicker of starlight to the fading of reality's final giants. What happens when black holes, the universe's most enduring structures, finally give way to quiet? How can something emerge from the stillness that remains? What does it feel like to reflect on the true end of everything? Our universe today is a brilliant tapestry of light, a grand cosmic city illuminated by countless stellar furnaces. Each star is a vast engine, tirelessly crushing atoms of hydrogen together in its core to forge heavier elements and release the energy that makes life possible. This is the stellar era, a time of vibrant creation and constant change. But this golden age of light is not permanent. It is a chapter with a definitive end. Over timescales so vast they defy comprehension, trillions of years from now, the raw material for new stars will finally run out. The great galactic reservoirs of hydrogen gas will be depleted, and the process of star birth will grind to a permanent halt. The last generation of stars will eventually burn through their fuel, their brilliant fires fading one by one across the cosmos. What they leave behind are the faint, cooling embers of their former selves. The sky will become populated by the quiet remnants of stars, white dwarfs and neutron stars, slowly releasing their remaining warmth into the expanding darkness. This monumental shift marks the end of the stellar era, often called the stelliferous era. It is the closing of a luminous epoch, a pivotal transition from a universe of light to one of deepening shadow. As the final starlight vanishes, we cross a threshold into the next unimaginably long chapter, the Degenerate Era, where the universe is ruled not by fire, but by cold, degenerate matter. This new dark age is governed by the quiet, patient physics of degenerate matter. The most common objects in this era are white dwarfs, the Earth-sized cores of stars from a much earlier time. They are not made of fire, but of a truly unique, ultra-dense form of matter where electrons are packed together as tightly as the laws of physics will allow. These cosmic embers no longer generate energy. They only radiate away the faint warmth left over from their formation. Their cooling process is almost unbelievably slow. Over timescales that far exceed the entire history of the universe up to this point, a white dwarf will gradually dim, its red glow fading to infrared and then to nothing. It will ultimately become a cold black dwarf, a frozen, crystalline sphere of carbon and oxygen drifting in total darkness. The cosmos is also dotted with the even denser remnants of massive stars, neutron stars. These are city-sized objects with masses greater than our Sun, their atomic nuclei crushed together into a superfluid sea of neutrons. And there are the failed stars, brown dwarfs, too small to ever ignite sustained fusion in their cores. In this vast, cold emptiness, a chance collision between two brown dwarfs might, on very rare occasions, create a single, temporary flash of new starlight. But these brief, isolated events are like a single match struck in a continent-sized dark room. They do nothing to halt the deepening chill. All the while, the universe itself continues its relentless expansion, stretching the fabric of space and driving the ambient temperature ever closer to the ultimate cold of absolute zero. This is the Degenerate Era, a chapter lasting for trillions upon trillions of years, defined by an epic stillness. Yet, even in this frozen quiet, the slowest and most subtle of processes are at work, processes that will ultimately dismantle the very fabric of matter itself. Yet even these frozen remnants are not eternal. The very bedrock of matter, the protons and neutrons that form atomic nuclei, may not be stable over the vast stretches of time we are now considering. According to some of our most ambitious theories in physics, the proton itself could have a finite lifetime. This idea comes from theoretical frameworks that attempt to unify the fundamental forces of nature. They suggest that over a timescale of 10,000 billion years, a proton might spontaneously transform. If this is true, then every object made of ordinary matter is living on borrowed time. A white dwarf, a cold and silent Earth-sized diamond in the dark, would not simply sit there forever. Its very atoms would slowly and quietly disintegrate. The protons at the heart of its carbon and oxygen nuclei would break apart, releasing a flash of energy and much lighter particles. This is not a violent explosion, but a slow, relentless fading. Over these staggering eons, every planet, every asteroid, every speck of dust that was not already drawn into a neutron star would simply fade away. All the complex structures left over from the age of stars would be erased, dissolving into a thin, cold sea of radiation and subatomic particles. This radical transformation marks the end of ordinary matter as we know it. It is important to note that proton decay remains a profound prediction, not yet confirmed by experiment. But its potential reality is crucial for understanding the ultimate fate of the cosmos. With the dissolution of all familiar matter, the stage is finally set for the universe's last and most enduring actors to take center stage. Only the most massive and gravitationally powerful objects will remain. Amid the fading of all ordinary matter, the black holes remain. These cosmic titans, born from the collapse of the most massive stars and the merging of galaxies, become the final macroscopic structures in the entire universe. For eons beyond counting, they are the sole anchors of gravity and complexity in a sea of expanding darkness. Their immense gravitational pull is the last organized force shaping the void around them. But even these giants are not truly permanent. They too are subject to a slow, inexorable decay, a process that unfolds over timescales so vast they challenge the very meaning of the word time. This process is known as Hawking radiation. The brilliant physicist Stephen Hawking theorized that the vacuum of space is not truly empty. It is a seething foam of virtual particles appearing and vanishing in pairs. Normally, these particle pairs cancel each other almost instantly, but at the very edge of a black hole's event horizon, the point of no return, something remarkable can happen. One particle of the pair might fall inward while the other escapes into space. From a distance, it appears as if the black hole is emitting radiation. To account for this energy loss, the black hole must surrender a tiny amount of its own mass. It is slowly fading away. The rate of this evaporation is incredibly slow and depends entirely on the black hole's size. A typical stellar mass black hole might take 10 to the power of 67 years to fully fade, but the supermassive black holes that anchor galaxies, like the one that once resided in the heart of the Milky Way, will persist for far, far longer. Their evaporation times are almost beyond comprehension, stretching to 10 to the power of 100 years or more. For nearly all of the Dark Era, these fading black holes are the only significant sources of energy in the cosmos. They are the final, dimming lighthouses in an ocean of nothingness. Their eventual disappearance, the moment the last black hole releases its final particle, marks the true and absolute end of structure. It is the beginning of the final act, a state of existence so empty and profound it has its own name, the Dark Era. This slow leak of energy, Hawking radiation, is a direct consequence of the strange rules that govern the smallest scales of reality. The vacuum of space is not a true emptiness. According to quantum theory, it is a vibrant sea of potential, where pairs of virtual particles flicker into and out of existence continuously. Most of these pairs annihilate each other almost instantly, but at the precipice of a black hole's event horizon, a different fate can unfold. One particle of the pair might be captured by the black hole's immense gravity, while its partner escapes into the vastness of space. From our perspective, the black hole has just emitted a particle. To conserve energy, the black hole must pay for this emission with an infinitesimal fraction of its own mass. It is a process of cosmic evaporation, one particle at a time. The temperature of this radiation is not random. It is precisely determined by the black hole's mass. A more massive black hole has a weaker gravitational pull at its event horizon, which results in a lower temperature. For a black hole with the mass of our Sun, this temperature is only a tiny fraction of a degree above absolute zero, making its energy loss almost undetectable. This is why the process is so incredibly slow for the giants we observe today. But as a black hole loses mass, a fascinating feedback loop begins. Its shrinking size makes its event horizon tighter, increasing its temperature. A warmer black hole radiates energy more quickly, which causes it to shrink faster, heating it up even more. This runaway process means that a black hole's life does not end with a whisper, but with a crescendo. In its final moments, after an almost eternal period of quiet decay, it would unleash a tremendous burst of particles and energy. This final flash is the black hole's last signature on a dark cosmos, a brief, brilliant farewell. This theoretical prediction is monumental because it sits at the crossroads of our two greatest physical theories, Einstein's general relativity and quantum mechanics. It suggests that black holes are not the eternal prisons we once thought, but dynamic objects with a temperature and a lifespan. By giving us a mathematical glimpse into how gravity and quantum effects intertwine, Hawking radiation offers a precious clue in the long quest for a theory of quantum gravity. With this mechanism in place, we can begin to map out the truly staggering timeline for the end of all black holes, and peer into the era that follows their final, silent departure. The lifespan of a stellar mass black hole is a number that defies all human intuition. For one with the mass of our Sun, the evaporation process would take approximately 10 to the power of 67 years. To even begin to grasp this scale, consider that the current age of our universe is only about 13.8 billion years. That is a 1 followed by only 10 zeros. The number 10 to the 67 is a 1 followed by 67 zeros, a duration so immense it makes the entire history of stars and galaxies feel like the briefest blink of an eye. And for the true giants, the supermassive black holes that once anchored galaxies, the timeline stretches to an almost meaningless 10 to the power of 100 years. These are not just long times, they are epochs that redefine the word forever. Throughout nearly all of this incomprehensible duration, the black hole's evaporation is a glacial process, emitting just a faint whisper of radiation. But this quiet decay does not last. As the black hole loses mass, a dramatic transformation occurs. Its event horizon shrinks, which in turn increases its temperature. A warmer black hole radiates more energy, which causes it to shrink even faster. This creates a runaway feedback loop, a crescendo of self-transformation. After an eternity of near silence, the black hole's final moments are sudden and spectacular. In the last second of its existence, it would release a titanic burst of energy, a final flash with the power of millions of hydrogen bombs detonating at once. This ultimate farewell takes place in a universe that is already profoundly ancient and dark, deep within the era named for that very darkness. When the last black hole vanishes in that brilliant, fleeting instant, it marks a transition more absolute than any that came before. With its departure, the final organized structure in the cosmos is gone. No more stars, no more planets, no more galaxies, and now no more black holes. What remains is a cosmos of pure, diffuse particles and radiation, a sea of near-nothingness expanding into an endless and silent future. The final flash from the last black hole signals a change more profound than any before. We have now entered the dark era. All the great structures that once defined the cosmos are gone. No galaxies drift in the void, no stars burn, and no planets orbit. The universe becomes a sea of near-nothingness, an expanse so empty and cold it challenges our very understanding of existence. The dominant inhabitants of this epoch are no longer objects, but the most fundamental particles and energy itself. The cosmos is filled with an incredibly dilute sea of photons, the particles of light. Many of these are the final remnants of Hawking radiation, released during the long evaporation of the last black holes. Other photons come from the complete decay of every proton and neutron that once formed atoms. But here, in this vast and expanding darkness, light itself is changing. The relentless expansion of the universe stretches the fabric of space, and in doing so, it stretches every photon traveling through it. This process, called redshift, systematically drains each photon of its energy, lowering its frequency over time. What was once a high-energy gamma-ray photon becomes a lower-energy radio wave, and then its energy dwindles further toward nothing. The entire cosmos is cooling toward the ultimate chill of absolute zero. In this profound quiet, other particles might make fleeting appearances. Electrons and their antimatter counterparts, positrons, could be all that is left of tangible matter. On exceedingly rare occasions, an electron and a positron might be drawn together by their opposite charges, forming a short-lived atom known as positronium. This atom is inherently unstable, and it would almost instantly annihilate, releasing a final, faint burst of energy before vanishing back into the void. These events are like single, isolated raindrops falling in an endless, silent ocean. They do nothing to halt the overall trend toward stillness. Time itself, in this era, may lose all familiar meaning. With no macroscopic events, no orbits, no decays of large objects, there are no clocks to measure its passage. The universe approaches a state of near equilibrium, a sameness that stretches forward without change. This is the quietest and most desolate phase of cosmic history, a chapter defined by the absence of everything that makes a universe recognizable. Yet, even here, at the very edge of physical processes, our theories allow us to peer even further into the abyss, to consider what might happen when even this dilute sea of particles faces its own ultimate fate. Even the most fundamental building blocks of reality are not safe in this deepening chill. The electrons and their antimatter twins, the positrons, are the last potential seeds of structure. Yet, in a cosmos stretched thin by relentless expansion, they face a lonely fate. If they are perfectly stable, as our current models suggest, they will simply drift forever. The space between them will grow at such a rate that they can never find each other again, becoming isolated islands in an ever-widening sea of emptiness. Their electrical attraction, once a powerful force binding atoms, becomes meaningless over these cosmic distances. If the earlier process of proton decay has already occurred, then this sparse sea of leptons and photons is all that remains of a once vibrant cosmos. But our understanding may not be complete. Some speculative theories in particle physics suggest that even the electron, a particle we consider a fundamental cornerstone, might itself be unstable over timescales that dwarf even the age of black holes. This idea pushes the limits of current science, but it highlights a profound truth. In the dark era, no form of matter can be assumed to last forever. Streaming through this emptiness are countless neutrinos, the ghostly particles that have barely interacted with matter since the universe's first second. They will continue their silent journey, unaffected by the dissolution of everything else, passing through the void as if it were not even there. The cosmos is now approaching its final equilibrium state. This is a condition physicists call maximum entropy. It is the ultimate state of disorder, a soup of ultra-low energy particles so evenly spread and so cold that no further work can be extracted. No new structures can ever form, and no significant physical changes will ever happen again. It represents the end of the universe's capacity for story, for change, for anything we would recognize as an event. This seems to be the absolute end of the line for matter, a final, quiet state for all that ever was. Yet, the most theoretical realms of physics propose that this profound silence may not be the very last word. There exists a hypothetical, more dramatic finale, one that hinges on the stability of the vacuum of space itself. But there is another potential finale, one far more abrupt than the slow fading of light. This scenario rests on a profound and thought-provoking possibility. The very fabric of our reality, the space that makes up the universe, might be built on a foundation that is not entirely settled. The key to this lies in the Higgs field, an invisible energy field that fills all of space and gives particles their mass. Our current observations suggest this field might not be in its most stable, lowest energy state. Instead, our entire cosmos could be existing in what physicists call a false vacuum, a condition of temporary but delicate balance. Imagine it like a ball resting in a small dip on the side of a much larger valley. It seems stable for now, but it is not at the true bottom. A single, random quantum event, a process known as quantum tunneling, could provide the nudge needed to push that ball out of its shallow bowl. It would then roll down into the true, deeper valley of the lower energy state. In cosmic terms, this event would trigger a bubble of true vacuum. This bubble would expand at the speed of light, and its wall would be a wave of fundamental change. As this wavefront moves, it would rewrite the very laws of physics within its sphere. The constants we take for granted, like the strength of gravity or the nature of atomic bonds, would be completely transformed. Every structure it encounters, from atoms to planets to any lingering black holes, would be instantly reorganized. There would be no warning and no escape. The probability of such an event occurring in our local region of space is almost zero over timescales of trillions of years. But in a universe that persists for an effectively endless duration, the odds shift dramatically. Given enough time, a quantum fluctuation triggering vacuum decay might not just be possible, it could become a statistical certainty. This offers a starkly different conclusion to the cosmic story, a sudden and total shift that stands in dramatic contrast to the epic, slow-motion quiet of the heat death. It is a reminder that the ultimate fate of all matter may not be a gentle fading, but a final, instantaneous transition. These two possible endings for our universe offer dramatically different finales. The first, known as the heat death or the Big Freeze, is the path we have been following so far. It is a quiet, gradual conclusion driven by the relentless expansion of space. In this scenario, the universe simply continues to stretch and cool. spreading all matter and energy ever thinner until it reaches a state of maximum entropy. This is a condition of perfect, uniform stillness where the temperature is the same everywhere, approaching absolute zero. No energy can flow, no work can be done, and no new structures can ever form again. It is a universe that has run its course, ending not with a bang, but in an epic, everlasting whisper. This is the fate that leads directly into the profound silence of the dark era we just explored. The other possibility is far more intense. It is called the Big Rip. This scenario hinges on a specific and potent form of the mysterious force we call dark energy. Dark energy is what drives the universe's expansion to accelerate. In most models, this acceleration is constant, but in the Big Rip hypothesis, dark energy would grow stronger over time. Its repulsive force would not just push galaxies apart, it would eventually overcome every force that holds things together. First, it would separate galaxy clusters, then individual galaxies. As the force intensifies, it would pull stars from their solar systems. Later, it would draw planets apart. In its final moments, this immense force would break apart stars and planets themselves. Then it would overcome the nuclear forces binding atomic nuclei, and finally, even the forces holding protons and neutrons together. The very fabric of every atom would be separated in a final, instantaneous flash. Current observations of the cosmos suggest that a Big Rip is not the most likely outcome. The evidence we have points toward a constant dark energy, which favors the long, slow fade of the heat death. Yet, the true nature of dark energy remains one of cosmology's greatest mysteries. Its potential to evolve means we cannot completely rule out a more dramatic end. Both of these theories, for all their differences, lead to the same ultimate destination, a cosmos without any of the complex structures we recognize. One does it through an epic, slow-motion dissolution, while the other accomplishes it in a sudden, intense finale. This understanding frames the entire timeline we are tracing, showing that whether the end comes through infinite cold or immense force, the journey for all matter leads toward a final, irreversible simplicity. Yet within this profound and final stillness, the laws of quantum mechanics whisper of a deeper truth. The void is not truly empty. According to the Heisenberg uncertainty principle, space itself is a seething, restless sea of potential. At the tiniest scales, pairs of virtual particles spontaneously flicker into existence, borrowing energy from the vacuum for a fleeting moment before meeting and vanishing. In our current universe, this quantum foam is a background hum, completely overshadowed by the brilliance of stars and galaxies. But in the eternal dark era, it becomes the only event of significance. Over timescales so vast they border on the infinite, these random fluctuations are not confined to creating mere particle pairs. Through a process called quantum tunneling, a sufficiently large and complex fluctuation could theoretically assemble almost anything. It could spontaneously generate a single, lonely hydrogen atom out of the void. It could, with unimaginably lower probability, conjure a perfect, frozen statue of a person. Or, in the most mind-bending speculation of all, it could momentarily assemble a fully formed, conscious brain, complete with impressions of a life that never was. Physicists call such a hypothetical entity a Boltzmann brain. The idea is that in a universe that exists for long enough, every possible random arrangement of particles, no matter how unlikely, will eventually occur. The spontaneous formation of a conscious observer in a silent cosmos becomes not just possible, but statistically inevitable if you wait long enough. This is not a prediction that such minds will actually appear, but a profound philosophical puzzle about the nature of probability, awareness, and time. It invites us to consider a deeply thought-provoking question. If a universe can, by pure random chance, create a solitary mind that believes it is living in a rich, structured world, how can we be certain that our own reality is not just such a fleeting fluctuation? Most physicists resolve this paradox by concluding that the conditions needed to create a stable, complex universe like our own are far more probable than the random assembly of a single, isolated mind. But the mere fact that we can entertain the thought highlights the sheer strangeness of the cosmos in its final epoch. In a reality where time has lost all meaning, the distinction between what is real and what is a random, momentary flicker begins to soften. This leads us to the final and perhaps most fundamental character in our story, time itself, and what role it could possibly play when all change has ceased. This final equilibrium, this state of maximum entropy, presents the most subtle and profound ending of all. The very arrow of time, the direction from past to future that seems so absolute to us, may itself fade into irrelevance. Our experience of time is not driven by a mysterious ticking, but by the flow of energy from places of high concentration to places of low concentration. A cup of coffee cools, a star burns its fuel, a memory is formed and then released. These are all processes that increase the overall dispersal of energy in the universe, and they give time its one-way direction. But in the Dark Era, that flow has reached its conclusion. The cosmos is now an almost perfectly uniform sea of particles and radiation, all at nearly the same ultra-low temperature. With no hot places and no cold places, there is no energy left to flow. There are no cups to cool, no stars to shine, no processes left to create structure or hold a memory. In this state, the physicist Sean Carroll and others have suggested, the very concept of time may lose its meaning. What does a second mean when there is no change to measure it against? What separates the past from the future when the state of the universe is identical for 1 trillion years and then for another trillion? The universe would not be aging, it would simply be. It would be static, a single, enduring frame in the cosmic story. This challenges our deepest intuitions. We are used to time as a river flowing relentlessly forward. But in this final state, the river has reached a vast, motionless ocean. There is no forward or backward, only an endless, featureless now. The end of time is as profound a transformation as the end of matter itself. It represents the ultimate stillness, a state of being where the very engine of change has finally come to rest. Contemplating this timeless state forces us to ask what reality even is without the progression of events that gives it structure and meaning. This leads us from the physical story of transformation to the deepest philosophical implications of the cosmos's ultimate fate. This cosmic quiet forces a question that echoes far beyond physics. If every structure, every memory, and every trace of life is destined to dissolve into an endless equilibrium, can anything truly be said to have lasting meaning? This is the profound philosophical shadow cast by the heat death of the universe, a challenge to our deepest intuitions about purpose. Some thinkers look upon this ultimate fate and see a universe that is inherently indifferent, a grand stage where the final curtain closes on every actor and every story, leaving no audience behind. From this perspective, any meaning we find is a temporary, local phenomenon, a beautiful but fleeting anomaly in a cosmos headed for permanent silence. Yet others draw a very different conclusion. They argue that the eventual end does not erase what comes before, but rather makes the transient beauty of existence all the more precious. The brief, brilliant flash of a star, the intricate dance of life on a planet, the profound depth of human consciousness, these are not diminished by the eventual darkness. Their value is inherent in their happening, not in their permanence. This view finds a powerful echo in ancient traditions across many cultures, which have long contemplated the impermanence of all things. The Japanese concept of mono no aware, for instance, is a gentle sadness for the passing of things, coupled with a deeper appreciation for their fleeting beauty. The scientific story of cosmic end gives this ancient wisdom a staggering new scale. It invites us to consider that meaning might not be a destination written in the stars, but something we create and live right here, right now. Our struggles, our loves, our art, and our curiosity become the universe's way of experiencing itself, however briefly. This perspective transforms the immense timeline from a sentence of futility into a call to action. It asks us what legacy we wish to build with the astonishing gift of consciousness during this singularly bright chapter in cosmic history. This reflection on legacy and the value of a temporary existence naturally leads us to ponder an even more ambitious idea: the possibility of life finding a way to persist against the dying of the light. Could the spark of consciousness outlast the stars themselves? This question leads us to one of the most audacious ideas in all of futurism: the possibility of an eternal intelligence. As the universe grows cold and dark, a truly advanced civilization might not simply accept its fate. Instead, it could embark on the ultimate engineering project, learning to survive by harvesting the last remnants of free energy. Visionary physicist Freeman Dyson imagined such a civilization building vast, gossamer-thin structures around the final black holes. These megastructures would capture every last photon of Hawking radiation, using the slow, steady evaporation of a black hole as a power source for billions upon billions of years. In a cosmos with no stars left to fuel them, these fading titans would become the last power plants in existence. The civilization relying on them would face a profound adaptation. As the universe cools and the energy flow diminishes, to avoid using more power than is available, this society would have to slow down. Its collective thoughts, its computational processes, its very experience of reality would gradually decelerate. A single thought might take a year, then 1,000 years, then 1,000,000 years to complete. Yet, in principle, the flicker of awareness could continue. This leads to an even more profound concept known as substrate-independent minds. The idea is that consciousness is not inherently tied to the squishy, biological wetware of a brain. It is a pattern of information, a specific, complex organization of data and processing. If that pattern could be replicated or sustained on any suitable substrate, like a vast, cool computer network, then the physical form becomes irrelevant. In the far future, minds might exist as shimmering patterns of light in orbiting data banks, or as intricate vibrations in the fabric of spacetime itself, running on the faint energy harvested from quantum fluctuations in the seemingly empty void. This is, of course, deeply speculative, a thought experiment at the very edge of science, yet it offers a powerful counter-narrative to the story of inevitable cosmic extinction. It suggests that information and mind might be the universe's most resilient creations, capable of persisting long after the last atom has decayed, finding a way to witness the silent depths of eternity. This vision transforms the ultimate fate of matter from a story of loss into a potential saga of persistence, where the legacy of life is not its physical form, but the enduring pattern of its intelligence. But what of the unseen architects of this cosmic destiny? The fate of all matter is woven together with the mysterious components that make up most of our universe: dark matter and dark energy. Together, they account for about 95% of everything that exists, yet their true nature remains one of science's greatest puzzles. Dark matter acts as the universe's invisible framework. Its gravitational pull is the main force that drew together the first galaxies and clusters, providing the structure upon which all visible things were built. Without its unseen influence, the cosmic city of stars and galaxies we know today could never have taken shape. Yet, as we look to the far future, its role may change. If dark matter particles are stable, they will simply continue to drift through the expanding emptiness, their gravitational influence fading as all the structures they helped create slowly fade away. However, some ideas suggest dark matter itself might not last forever. It could slowly transform over eons, adding a final, gentle trace of energy to the cooling cosmos. The true guide of the final state, however, is dark energy. This mysterious force is not a pull, but a push, an inherent quality of empty space that causes the universe's expansion to speed up. Its steady pressure is what actively reshapes the cosmic landscape, pulling galaxy clusters apart and ensuring that the universe grows ever colder and more spread out. In the scenario of the heat death, we imagine dark energy remains constant, a steady influence leading to that ultimate, quiet balance. But what if it changes? Our current knowledge is incomplete. If dark energy were to weaken and reverse its effect, the universe could potentially draw back together in a fiery big crunch. On the other hand, if it were to grow stronger over time, it could lead to the dramatic end of a big rip, pulling apart the very fabric of reality long before black holes have a chance to vanish. This deep uncertainty reminds us that the timeline we have traced is a map drawn with the best information we have, but huge territories of the unknown still lie ahead. The final moments of the universe are not yet a settled story. They depend entirely on the nature of these dark components, whose secrets we are only beginning to understand. This is not an end to our curiosity, but an invitation to look deeper, to question what we think we know about the fundamental forces that will one day decide the fate of everything. This paradox strikes at the very heart of our understanding of reality. Hawking radiation presents a puzzle so profound it is known as the black hole information paradox. The rules of quantum mechanics are built on a fundamental principle that information is never truly destroyed. If you were to burn a book, every single letter and word of that story would, in principle, be preserved in the precise arrangement of the smoke and ash particles. The information is scrambled, but it is not gone. Now apply this to a black hole. Imagine a star, a planet, or an entire encyclopedia falls past the event horizon. According to Hawking's original calculations, the radiation that slowly leaks back out is completely random, carrying no specific details about what fell in. It is like thermal noise, a hiss of undifferentiated energy. When the black hole finally evaporates in that last flash, what then happens to the intricate information about that star, that planet, or that book? If it is truly lost forever, it would mean that the most fundamental law of quantum mechanics is broken. This is the paradox, a direct contradiction between our two most successful theories, gravity as described by Einstein and the quantum rules that govern the small. It suggests that one or both of these pillars of physics is incomplete where they meet at the precipice of a black hole. So how could this be resolved? One compelling idea is that the information is not lost at all, but is somehow subtly encoded or imprinted onto the Hawking radiation itself. The radiation would not be perfectly random, but would contain incredibly faint, complex patterns that record the history of everything that ever fell into the black hole. When the black hole vanishes, this encoded story is released back into the universe, preserving the cosmic ledger. Another possibility is that the evaporation process does not go to completion. Perhaps a tiny, stable remnant is left behind, a cosmic cinder no larger than a fundamental particle, which contains within its structure the compressed information of everything the black hole ever consumed. Solving this puzzle is not just an academic exercise, It is vital for the quest to find a theory of quantum gravity, a framework that would finally unite the worlds of the very large and the very small. The implications stretch across the entire lifespan of the cosmos. If information can be lost, then the final state of the universe in the Dark Era is one of true and permanent forgetting. But if information is always preserved, then in some deeply fundamental way, the story of every star, every planet, and every conscious moment is eternally woven into the fabric of reality, even after the last light has faded. This struggle to understand what happens to a story inside a black hole may ultimately reveal the deepest rules governing the final fate of all existence. Deep within the silent era ruled by degenerate matter, a final, slow-burning drama is unfolding among the coldest objects in existence. These are the black dwarfs, the ultimate end state of stars like our Sun. After white dwarfs radiate away their last vestiges of heat over trillions of years, they do not simply vanish. They enter a new phase as black dwarfs, Earth-sized spheres of crystallized carbon and oxygen, colder than the cosmic background itself, drifting in perfect darkness. They appear to be the most inert objects imaginable, frozen into a state of near absolute zero. Yet, even here, the ghostly rules of quantum mechanics promise one last spectacular transformation. Inside a black dwarf's core, atomic nuclei are packed tightly together, but the intense cold has robbed them of the energy needed to overcome their mutual electrical repulsion and fuse. In a living star, immense heat and pressure force this fusion to happen. In a black dwarf, that energy is gone. This is where quantum tunneling enters the story. This is a bizarre but fundamental process where a particle can, by pure chance, bypass an energy barrier instead of going over it. It is as if a ball resting in a bowl could, once in a great while, spontaneously appear on the other side of the bowl's rim without having rolled up and over. For the nuclei in a black dwarf, this quantum effect means that over truly cosmic timescales, fusion is still possible. The dominant element in an old black dwarf is iron, the ash of previous stellar burning. Through quantum tunneling, these iron nuclei can very slowly fuse into even heavier elements like nickel. But this type of fusion does not release energy, it consumes it. It acts as a subtle sink, gradually pulling energy out of the star's core. This slow, quiet process destabilizes the delicate balance that has supported the black dwarf for eons. The core, having lost the tiny amount of energy that was preventing a sudden collapse, begins to implode under its own immense weight. The result is a titanic thermonuclear explosion, a supernova ignited not by the frantic final moments of a young, massive star, but by the patient, accumulated whispers of quantum chance. This event, a black dwarf supernova, would be the very last fireworks display in the entire cosmos. The timeline for this is almost beyond numerical description, occurring around 10 to the power of 1,100 years in the future. To call these events rare is a profound understatement. In an epoch where galaxies have dissolved and black holes are the only remaining landmarks, a single black dwarf supernova might be the only significant source of light in a volume of space larger than our entire observable universe is today. For a brief, brilliant moment, this silent, dark expanse would be torn by a light more powerful than a billion suns, a final echo of stellar energy in a universe that had long moved beyond such intensity. These isolated transformations are the ultimate demonstration that, given enough time, the subtle, probabilistic nature of reality can orchestrate the most dramatic of changes, offering one last glimpse of cosmic splendor before the long reign of the black holes truly begins. Even in the profound stillness of the Degenerate Era, the cosmic clock is still ticking. The quiet dance of orbital systems continues, but it is a dance with an inevitable conclusion. Planets still circle the frozen embers of their parent stars, and binary pairs of white dwarfs or neutron stars still revolve around one another in the dark. These gravitational partnerships, however, are not everlasting. They are slowly, almost imperceptibly, losing energy. The mechanism for this gradual change is gravitational radiation, a subtle prediction of Einstein's theory of general relativity. Any massive object that accelerates, like a planet in its curved orbit, creates ripples in the very fabric of space-time. These ripples, known as gravitational waves, carry energy away from the system. The effect is minuscule, almost negligible over human timescales, but over the eons that define the Degenerate Era, it becomes the dominant force reshaping these isolated systems. Imagine a marble rolling around a vast, shallow bowl in a room of perfect silence. Each time it completes a circuit, it loses a single, infinitesimal grain of its energy to the faintest whisper of sound. Over millions of years, the marble's path would tighten, its orbit shrinking until it finally comes to rest at the very center. This is the future awaiting every orbital system in the darkening cosmos. For a planet like Earth, if it had survived the Sun's earlier expansion, its orbit would decay over a timescale of 10 to the power of 20 years or more. It would spiral ever closer to the cold, dark dwarf that was once our Sun, until a final, quiet union brought its long journey to a close. This slow dissolution of gravitational bonds is a fundamental driver of entropy, the universe's measure of disorder. As orderly orbits decay into single, merged objects, the cosmos moves one step closer to a state of perfect uniformity. It is a quiet prelude to a far grander transformation, the gradual dispersal of the galaxies themselves. Galaxies, those grand cities of stars we see scattered across the night sky, are themselves temporary, held together by the mutual gravitational pull of their countless stars and the immense halos of dark matter surrounding them. They seem like permanent fixtures of the cosmos. But on the timeline of the Degenerate Era, their foundations are slowly being chiseled away. The primary engine of this galactic dissolution is a quiet, relentless process known as dynamical relaxation. Within a galaxy, stars are in constant motion, a swirling dance of billions of partners. As they pass by one another, their gravitational fields interact, subtly tugging and altering each other's paths. These gentle nudges, repeated over trillions of orbits, act like a cosmic game of billiards. The cumulative effect is a slow but steady redistribution of energy among the stars. Some stars gain energy, moving into wider, slower orbits. Others lose energy, sinking closer to the galactic center. And a few, at the far end of this statistical exchange, can gain so much velocity that they achieve escape velocity. They are flung clear of their galactic home entirely, cast out into the immense darkness of intergalactic space to drift forever in solitude. This is the evaporation of a galaxy, not in a fiery cataclysm, but in a silent, gradual dispersal. Over a timescale of 10 to the power of 19 to 10 to the power of 20 years, a galaxy like our own Milky Way will have lost the vast majority of its stellar remnants to the void. What remains is a sparse, diffuse cloud of the unluckiest objects, those that never received the gravitational kick needed to break free, slowly circling the supermassive black hole at the center until they too are consumed or scattered. This same fate awaits the largest structures of all, galaxy clusters. These vast families of hundreds or even thousands of galaxies are also gravitationally bound. Yet they face a dual threat. Their own internal dynamics can eject entire galaxies from the cluster, much like stars are ejected from a single galaxy. More significantly, the relentless expansion of the universe, driven by dark energy, continuously stretches the space between the cluster's members. the gravitational glue that holds the cluster together is steadily overwhelmed by the ever-growing cosmic distances. The cluster gently pulls apart, its constituent galaxies spreading out into the ever-cooling expanse. The evaporation of galaxies and the dispersion of their clusters represent a monumental shift. It is the end of the largest organized structures that gravity will ever build. The universe, once a tapestry of brilliant islands and archipelagos of light, becomes a uniform, dark sea where isolated stars and their remnants are separated by voids of incomprehensible scale. This great dispersal is a critical step toward the final equilibrium, setting the stage for the long, solitary reign of the universe's final titans. Even the universe's ultimate cosmic diamonds are not built to last forever. Neutron stars, the incredibly dense cores left behind after a supernova's immense energy, will also face their own quiet end. A city-sized object containing more mass than our Sun, a neutron star stands as a testament to the raw power of gravity, where matter has been compressed into a sea of neutrons so dense that a single teaspoonful would weigh billions of tons on Earth. Yet, in the deep time of the Degenerate Era, these remarkable objects are not permanent fixtures. The first path to their end relies on the slow transformation of the proton. If this process is real, then the very neutrons that give these stars their name and structure are living on borrowed time. A neutron, when isolated, is unstable and will transform into a proton, an electron, and an antineutrino in a matter of minutes. Inside a neutron star, the immense gravitational pressure prevents this change, locking the neutrons in a stable state. But if the proton itself can transform, then this stability is an illusion. Over eons, the protons that would be created from neutron transformation would themselves disintegrate. The entire star would slowly unravel from the inside out, its incredible density fading away as a gentle stream of particles and energy until nothing of its form remained. This would be a dissolution so gradual and patient it would make the cooling of a white dwarf seem rushed by comparison. But what if protons are perfectly stable and never transform? Even then, a neutron star's fate is sealed. Its incredible birth leaves it blazing with heat, but over trillions of years, it will radiate this energy away, cooling into a solid, ultra-dense sphere even colder than the surrounding space. Its rapid rotation, often hundreds of times per second, is also not eternal. By emitting gravitational waves and electromagnetic radiation, a pulsar's spin is gradually braked, its lighthouse beam slowing until it finally fades, leaving a dark, still sphere. Its powerful magnetic field, capable of bending atoms themselves, will also slowly weaken and dissipate. In the profound quiet of the darkening cosmos, chance encounters still occur. A wandering black dwarf or another neutron star could, on a timescale of epic rarity, drift close enough for a gravitational dance. Such a meeting would be a final, spectacular event, likely resulting in the formation of a new black hole, a larger resting place for the memory of two ancient stars. Beyond these classical ends, more exotic transformations are theoretically possible. The immense density inside an old, cold neutron star might provide the conditions needed to break down neutrons themselves into their constituent parts, a soup of up, down, and strange quarks. This could trigger a phase transition, turning the entire star into a single, city-sized droplet of strange quark matter, an exotic substance that would be the most stable form of matter in the universe. Whether they fade away through particle transformation, cool into absolute stillness, or change into something entirely new, the ultimate transition of neutron stars is a quiet but monumental event. It represents the passing of yet another class of complex object, a further simplification of the cosmos as it moves toward its final, featureless state. There is a breathtaking possibility that our entire cosmos is just one leaf on an infinite, ever-growing tree. This is the concept of eternal inflation, a vision of reality where the journey of the universe is not a single story with one ending, but an endless cycle of birth and transformation. The idea builds upon the theory of cosmic inflation, the notion that our universe underwent a fantastically rapid expansion in its first moments. In an eternally inflating multiverse, this process never truly stops. Think of it as a vast, bubbling cosmic ocean. Most of this ocean is a seething, expanding froth, a state of hyper-fast inflation. But every so often, in a random patch, the inflation process slows down and stops. When that happens, the energy driving the expansion is released, igniting a hot Big Bang and creating what we call a pocket universe, a self-contained realm with its own laws of physics. Our entire observable universe could be just one such pocket, a single bubble in an infinite, churning foam. While our bubble may cool into the deep quiet of a long cosmic future, the inflating background continues its relentless expansion, constantly giving rise to new bubbles, new universes, each with its own unique properties. Some of these pocket universes might form only briefly or possess laws that make complexity impossible. Others might be lush and long-lived, filled with stars, galaxies, and perhaps even life. In this grander picture, the end of our specific universe is not the end of everything. It is simply the closing of one chapter in a story with an infinite number of pages. Life and consciousness may not be unique to our bubble, but could be flourishing in countless other pockets across the multiverse, a cosmic flame that is forever passed from one realm to the next. This perspective offers a form of continuity, not for us as individuals or even for our home universe, but for the processes of creation and complexity themselves. The cosmos as a whole becomes an engine of perpetual renewal, where the concepts of a final beginning and an ultimate end lose their meaning. This vision transforms the profound silence awaiting our universe from a final conclusion into a single, quiet note in an endless, universal symphony. The grand cosmic story we have traced is a map drawn with the best tools we have today, but it is not the final word. Our current understanding of physics, while incredibly powerful, has its limits. The theories of general relativity and quantum mechanics work flawlessly within their own domains, the vast cosmos and the tiny quantum world, but they famously refuse to speak to one another at the edge of a black hole or the moment of the Big Bang. This fundamental divide means our predictions for the ultimate fate of all matter are necessarily incomplete. We are trying to read the final chapter of a book without fully understanding the alphabet it is written in. To see beyond the heat death or the Big Rip, we require a theory of quantum gravity, a single framework that can describe the force of gravity under the unique rules of the quantum realm. Several candidates are vying for this title, each offering a different vision of the end. String theory, for instance, suggests that the fundamental building blocks of reality are not points, but incredibly tiny, vibrating strings. Their unique vibrations could give rise to every particle and force we see, potentially revealing new states of matter or energy that become relevant only in the universe's final moments. Another approach, loop quantum gravity, proposes that space itself is woven from a network of finite loops. In this view, the universe might not be able to collapse to an infinitely dense point, suggesting the possibility of a cosmic bounce. This opens the door to a cyclic universe where our Big Bang was not a true beginning, but a rebirth from a previous phase of contraction. Our current timeline, ending in silent darkness, could simply be one season in an endless cycle of expansion and renewal. The crucial point is that without a complete theory, our vision of the far future remains a compelling sketch, not a finished painting. the true story will be written by future discoveries. The measured value of dark energy, a single number that dictates the expansion rate of the universe, will determine whether we drift apart gently or are pulled apart. The stability of the proton, a question that particle physicists are still trying to answer, will decide whether all matter eventually fades away or endures in some form. Acknowledging these boundaries is not a weakness of science, but its greatest strength. It is an honest admission of how much we have yet to learn, and it points directly toward the most exciting frontiers of research. The ultimate fate of the cosmos is not a closed book, but a living mystery, one whose solution may reveal that our universe holds possibilities far stranger and more wonderful than anything we can currently imagine. This vast cosmic timeline invites a deeply human question, with the understanding that every structure from a star to a galaxy is transient. What is our purpose here and now? We find ourselves in a brief, brilliant sliver of cosmic time, a species gifted with awareness during the universe's most vibrant chapter. This unique position calls for an ethical consideration that reaches beyond our world. Should humanity or any intelligent life strive to become a guardian of consciousness itself, working to extend its light for as long as the physical laws allow? Thinkers like Nick Bostrom have described this as a cosmic responsibility, an invitation to protect the future of mind. This perspective sees life not as a fleeting accident, but as the universe's most remarkable creation, something worth nurturing across the ages, perhaps by reaching toward other worlds or learning to draw energy from the final fading black holes. It is a call to action on a truly grand scale. Yet there is another, equally profound response. It is the philosophy of embracing transience. The undeniable fact that all things must end can deepen our appreciation for the present moment, for the beauty of a sunset, the richness of human connection, and the simple wonder of being here at all. This view does not see our temporary nature as a reason for sorrow, but as the very source of meaning. It encourages us to focus on creating beauty, fostering understanding, and living with purpose right now, rather than focusing only on a distant, uncertain future. These two perspectives are not necessarily in conflict. They represent a fundamental dialogue about our role in the cosmos, a conversation that connects the clear equations of scientific cosmology to the warm, beating heart of human values. This ethical dimension adds a crucial layer of depth to the scientific story. It asks us to consider not only what will happen to the universe, but what we, as its temporary aware inhabitants, should do with the extraordinary gift of our existence. This reflection on legacy and meaning brings us to one final, breathtaking possibility, a vision where the universe itself might not be content with a single, silent finale. So much of what we build is meant to last, yet we know it cannot. But what of our thoughts, our knowledge, our greatest works of art and science? While every physical record will eventually dissolve, from digital servers to stone tablets, the information they contain might achieve a different kind of longevity. The laws of physics suggest that information itself is never truly destroyed, only transformed. In a universe destined for maximum disorder, this principle offers a glimmer of permanence. The data comprising a symphony, a mathematical proof, or a recorded history could, in theory, be translated. Imagine encoding the complete works of human culture into the spin of subatomic particles, or imprinting it onto the fabric of spacetime itself. These are speculative ideas, of course, but they rest on a profound possibility. The essence of what we create may be separated from the fragile matter that first gave it form. This concept extends beyond our own universe. If we live within a multiverse, a vast collection of cosmic bubbles, then the ideas generated here could find resonance elsewhere. A mathematical truth discovered by a human mind is not a local invention. It is a universal constant, a pattern that would hold true in any reality with similar physical laws. In this way, the Pythagorean theorem or the laws of thermodynamics are not just human knowledge, they are permanent features of logical space, waiting to be uncovered. The impact of a powerful idea, once conceived, might ripple through the multiverse in ways we cannot comprehend. This perspective reframes our search for meaning. Our legacy may not be in constructing monuments that can withstand trillions of years, but in contributing to a timeless tapestry of understanding. The stories we tell, the beauty we capture, and the truths we uncover could achieve a form of immortality, not of stone but of pure information. This is not a promise, but a profound hope written into the most fundamental laws we are currently aware of. It suggests that the universe values the pattern of a thought as much as the particle that carries it. Our journey has brought us across an almost unimaginable expanse of time, from the final flicker of starlight to the silent fading of the last great structures in space. The ultimate destination for all matter appears to be a state of profound simplicity, a quiet and nearly still cosmos where change itself has ceased. This is not a dramatic conclusion, but a gradual and gentle transition into a timeless equilibrium. Yet, this scientific vision of a distant future does not diminish our present reality, it illuminates it. We are living in the cosmic springtime, a brief and brilliant window where the universe is filled with light, structure, and the emergence of conscious life. The very fact that we can trace this epic timeline, that we can ponder the ultimate fate of galaxies, is a testament to the extraordinary moment we occupy. This knowledge invites not despair, but a deep and humbling awe for our place in the grand story. It asks us to cherish the fleeting beauty of a starry night, the complexity of a living cell, and the profound power of a curious mind. What are your thoughts on this cosmic destiny? Let us know in the comments, and if you want to continue exploring the great mysteries of space and time, be sure to